This is our second lecture about the Laplace transform. First, we'll solve some more initial value problems using the theory that we developed last time, and then we'll look at step functions. First, a little bit of revision from the last lecture. We want to use the Laplace transform to solve a differential equation. I suppose we're starting with a difficult differential equation, and we don't know how to solve it directly. The method here is that we can use the Laplace transform to change our difficult differential equation into an easier equation, which we could then solve for capital Y. If we know capital Y, then perhaps we could take the inverse Laplace transform to find the answer that we're looking for, small y. And the key point here is that the Laplace transform eats derivatives. Anytime we have a derivative of a function in our differential equation, after we apply the Laplace transform, the derivatives disappear, and instead we just multiply it by s. But then this extra term, this extra initial condition term. We have a similar formula for the second derivative, the third derivative, or the nth derivative. And these are the key formulae we're going to be using to solve our differential equations. I'm going to be doing 3 examples, and the first one is use the Laplace transform to solve y double prime minus 3y prime plus 2y is equal to cos t with the initial conditions y of 0 is 0, y prime of 0 is equal to 0. I know this is not a difficult differential equation. We could solve this using the methods from chapter 3, but I want to use the Laplace transform to solve it. If you're given a question which says use a particular method to solve it, then you have to use that method. So to answer this question, we have to use the Laplace transform. What we do is we take the differential equation and we take the Laplace transform of everything. So the Laplace transform of y double prime minus 3 times the Laplace transform of y prime plus 2 times the Laplace transform of y is equal to the Laplace transform of cos. Using the theorem, we know the Laplace transform of y double prime and the Laplace transform of y. Using our table of elementary Laplace transforms, we know that the Laplace transform of cos t is s over s squared plus 1. Because the initial conditions are both 0, a lot of these terms will disappear, and we're just left with s squared minus 3s plus 2, capital Y, is equal to s over s squared plus 1. Divide both sides by s squared minus 3s plus 2 to solve for y. And I want to factorize this as s minus 2, s minus 1 on the bottom. If we can find the inverse Laplace transform of this function, then we've solved the initial value problem. To go further, we need to use partial fractions. So we're going to expect that this is something over s squared plus 1 plus something over s minus 2 plus something over s minus 1, where the somethings on the top are always polynomials of degree 1 less than the denominator. S squared plus 1 is a second degree polynomial, so on the top we should have a first degree polynomial, and so on. Multiply this all through to put this over the same denominator. I'll leave this for you to check. And then find a, b, c, and d. I'll just tell you the answers. I'll leave this for you to double check. I think that we must have a is 1 over 10, b is minus 3 over 10, c is 2 over 5, and d is minus a half. So we have that capital Y looks like this. 1 over 10s minus 3 over 10, all over s squared plus 1, plus 2 over 5 s minus 2, minus 1 over 2 s minus 1. Or we can split it up like this. 1 over 10 multiplied by s over s squared plus 1, because s over s squared plus 1 we can find on our table of elementary Laplace transforms. Likewise, 1 over s squared plus 1 is on the table, so take 3 over 10 out. 1 over s minus 2 is on the table, and 1 over s minus 1 is on the table. In fact, the first function is the Laplace transform of cos t. 1 over s squared plus 1 is the Laplace transform of sine t. 1 over s minus 2 is the Laplace transform of e to the power 2t. And 1 over s minus 1 is the Laplace transform of e to the power t. As soon as we get to this point, we can write down small y of t. Small y is the inverse Laplace transform of capital Y, so it must be 1 over 10 cos t minus 3 over 10 sine t plus 2 over 5 e to the power 2t minus a half e to the power t. What would the graph of this look like? Sine and cos, we know, go up and down. E to the power 2t, we know, goes up like this. And this is going to be dominant over e to the power t. The graph would look like this. For negative t, e to the power 2t and e to the power t are very, very small, so we can forget about those. The left-hand side is just sine and cos, so just going up and down. On the right-hand side, e to the power 2t is dominant, so the function curves up like this. Second of our 3 examples. This time another easy one. Use the Laplace transform to solve y double prime plus 2y prime plus y is equal to 4e to the power minus t. But now with the initial conditions, y of 0 is 2, y prime of 0 is minus 1. So what do? We start with the differential equation. And we take the Laplace transform of everything. And then we use the theorem that I mentioned earlier to write down the Laplace transform of y double prime and the Laplace transform of y prime. First, the Laplace transform of y prime is this green function. Instead of the Laplace transform of y double prime, which I've written in orange, we could write s squared capital Y minus s y0 minus y prime of 0, and so on. We put the initial conditions in. Instead of y0, we write 2. Instead of y prime of 0, we're going to write minus 1. Here we go. On the left side, we need to put all of the y terms together. I want to take the minus 2s plus 1 minus 4 to the right-hand side, and I want to factorize s squared plus 2s plus 1. So take this to the right, it becomes 2s plus 3. Factorize s squared plus 2s plus 1 to s squared plus 1 squared. Divide, put the right-hand side all over the same denominator, and then divide by s plus 1 squared. Capital Y is 2s squared plus 5s plus 7 over s plus 1 cubed. If we can find the inverse Laplace transform of this function, then we've solved the problem. We need to use partial fractions to find small y. I'm going to leave it for you to check that if we write our function as something over s plus 1 plus something over s plus 1 squared plus something over s plus 1 cubed, then a, b, and c must be 2, 1, and 4. We're going to take the inverse Laplace transform of this. I'm going to write this as 2 times 1 over s plus 1. 1 over s plus 1 is on the table, that's fine. Plus 1 over s plus 1 squared. Again, this is on the table, that's fine. 1 over s plus 1 cubed is not on the table, but 2 over s plus 1 cubed is on the table. So I'm going to take 1 factor of 2 out and leave 1 factor of 2 inside the bracket. If we look at our table of elementary Laplace transforms, we find that the first one is the Laplace transform of e to the power minus t. The second one is the Laplace transform of t, e to the power minus t. And the third bracket is the Laplace transform of t squared, e to the power minus t. As soon as we've found these, we've got our answer. Put everything together, simplify. The solution to the initial value problem is 2t squared plus t plus 2 multiplied by e to the power minus t. What does the graph of this function look like? If t is positive and large, then e to the power minus t is very, very small. So the right-hand side should be very, very small. If t is negative and large, 2t squared will be positive and large, and e to the power minus t will be positive and large. So on the left side, we expect the graph to curve up like this. And in fact, the graph of this solution does look like this. Our third and final example in this section, use the Laplace transform to solve 4 derivatives of y plus 2y double prime plus y is equal to e to the power 2t. With the initial conditions, y of 0 is 1, y prime of 0 is 1, y double prime of 0 is 1, and y triple prime of 0 is equal to 1. Now we have a 4th order differential equation to solve. I've put this problem at the top. We're going to take the differential equation and we're going to take the Laplace transform of it. Or we're going to be taking the Laplace transform of each part. The first one, the Laplace transform of the 4th derivatives of y, starts with s to the power 4, of course, capital Y, and then it goes s cubed, s squared, s, and so on. And the initial conditions go y 0, y prime 0, y double prime 0, y triple prime 0, and so on. For the green one, this is one we've used before, s squared capital Y minus sy 0 minus y prime of 0. The Laplace transform of e to the power 2t is 1 over s minus 2. Now remember, the initial conditions are all 1. So we can just remove these, and this one we can write as 1. Here we go. I want to gather all of the capital Y terms together. And then I want to move s cubed, s squared, s and 1 terms all over to the right-hand side. On the right-hand side, I want to put everything over s minus 2. Like this. And then I want to divide both sides by s to the power 4 plus 2s squared plus 1. And of course, s to the power 4 plus 2s squared plus 1 is the same as s squared plus 1 all squared. What do we do next? Next, we need to use partial fractions. I'm trusting that you know how to do this, so I'm just going to jump ahead and tell you the answer. Please check that I haven't made a mistake here. I think we get 1 over 25 over s minus 2 plus 24 over 25s plus 23 over 25 over s squared plus 1 plus 9 over 5s plus 8 over 5 over s squared plus 1 squared. Let's split this up like this. Now, do we recognize these brackets? The first three, which are now I've put in green, we know these ones. These are elementary ones. We've seen these before. These are on our table. E to the power 2t, cos t, and sin t. Okay, that's going to be easy. But what do we do about the last two brackets? What do we do with 2s over s squared plus 1 squared and 2 over s squared plus 1 squared? Let me remind you of a formula from last week. Remember that the Laplace transform of t, f of t, is minus capital F prime. We're going to use these to find these two inverse Laplace transforms that we want. So what do these look like? What do these look like they are the derivatives of? Well, they look like they're the derivatives of perhaps 1 over s squared plus 1, or maybe s over s squared plus 1. Something like the derivatives of these. So let's have a look at the Laplace transform of t sine t and the Laplace transform of t cos t. First one, the Laplace transform of t sine t is the same as minus the derivative of the Laplace transform of sine t, or minus the derivative of 1 over s squared plus 1, which is 2s over s squared plus 1 squared. Great, this is what we wanted. The first one must just be t sine t. Now let's look at the Laplace transform of t cos t. Using the formula, that's minus the derivative of the Laplace transform of cos t, or minus the derivative of s over s squared plus 1, which turns out, we could write this in many different ways, but I choose to write it as 1 over s squared plus 1 minus 2 over s squared plus 1 squared, which I leave for you to check. Now that's not quite what we want. There's a 2 over s squared plus 1 squared here. Okay. There's a minus sign. Minus sign doesn't matter. We can just multiply by minus 1 later. But we also have this extra term, this extra 1 over s squared plus 1. What is 1 over s squared plus 1? 1 over s squared plus 1 is just the Laplace transform of sine t. So we're going to be needing to remove this. So what I'm actually going to be looking at is the Laplace transform of sine t minus t cos t. Because then these 1 over s squared plus 1 terms are going to cancel out, the minus signs are going to cancel out, and then we're going to be left with our 2 over s squared plus 1 squared, which we want. So the two functions that we want are t sine t and sine t minus t cos t. Great. So now we're ready to write down our solution. We found that the inverse Laplace transform of 2s over s squared plus 1 squared is t sine t, and we found that the inverse Laplace transform of 2 over s squared plus 1 squared is sine t minus t cos t. We can use this just here. we have our formula for capital Y. And now we know what each term is, so now we can write down small y. Small y must be 1 over 25 e to the power 2t. For the green term, we have 24 cos t. For this red term, 23 sine t. The dark blue term, 9 over 10 t sine t. And for the light blue term, 4 over 5 sine t minus t cos t. This is the solution to the initial value problem. We could actually simplify this slightly more because we have 2 sine t terms. If we wanted to, we could do one extra step to combine these together to simplify our answer a little bit. I'm not going to do that here. Now, what does the graph of this function look like? We've got sine and cos terms. We know they go up and down. We've got t sine and t cos terms. These are also going to be going up and down, but the amplitude of the oscillations is going to increase with t. And we have an e to the power 2t terms. If t is a large positive number, e to the power 2t is going to be dominant. So the right-hand part of the graph is going to be curving up like this. If t is a negative number, then the t sine t and the t cos t terms are going to be the dominant terms. So we're going to expect our function to be going up and down between t and minus t, or some constant multiplied by these. Let's look at the graph that I drew using a computer. Here we go. On the right-hand side, e to the power 2t is dominant, so the function just curves up to infinity. On the left, the function oscillates up and down using t sine t and t cos t, and the amplitude increases as t becomes more negative. Okay, hopefully at least most of that section was revision for you. That was a continuation of the topics that we looked at last week. Now I want to start talking about step functions, which will be our topic for the rest of today's lesson. What is a step function? A step function is a function which looks like this. We have a horizontal part, and then it jumps up, and then we have another horizontal part. This step function is called the unit step function, and it can be written in different ways. I'm going to write this as u subscript c. Some people use the letter theta, and some people use the letter h. But for this course, I'm going to be using u subscript c, and I would prefer if you use the same notation in your answers. This is a function which is defined on the positive real numbers. First, the function is equal to 0, and then the function jumps up and is equal to 1. For example, draw the graph of 1 minus cos c. It looks like this. First of all, uc is equal to 0, so we get 1 minus 0, which is 1. And then after c, uc is equal to 1, we get 1 minus 1, or 0. Draw the graph of y is equal to u1 minus u2. Now, clearly 1 and 2 are important points. So we're going to be thinking about the function on 3 different intervals, between 0 and 1, between 1 and 2, and between 2 and infinity. So I want to break the function up like this. I'm going to be looking at these 3 intervals separately. We show you the graph, tidy this up a little bit. And then first I want to look at the graph of u1. First, this graph is equal to 0, this function 0. Between 1 and 2, the function is equal to 1. And then between 2 and infinity, the function is equal to 1. So we should get 0 here, 1, and then 1. Then I want to look at u2. Here we go. I've drawn the graph of u2 at the top. On the first interval, the function is equal to 0. On the second interval, the function is equal to 0. And then on the third interval, the function is equal to 1. So we would get 0, and then 0, and then 1. There we go. So on the first interval, we get 0 minus 0. Of course, that's just 0. On the middle interval, we get 1 minus 0, 1. And on the right-hand interval, we get 1 minus 1. That's 0. We're asked to draw the graph of this function. So here it is. The graph is 0, and then the graph is 1, and then the graph is 0. Write the function f of t, which is equal to 2, and then 5, and then minus 1 and 1, in terms of the unit step function. Let me show you a graph of this function. Here we go. Let's look at the first part first, the part which is at the moment drawn in blue. The function starts being equal to 2. So we expect our function to be 2 plus something. Let's go on to looking at what happens at 4. When t is equal to 4, the function goes up 3. It goes from 2 to 5, so it goes up 3. So in our function, we're starting at 2, and then when t is equal to 4, we go plus 3, up 3 or plus 3 at 4, or multiplied by u4. We haven't done the rest yet, so it's still plus something. What happens at 7? At 7, we go from 5 down to minus 1. We go down 6. So at 7, we're going to go minus 6. And because this is happening at 7, that's minus 6 u7. We haven't finished yet. We still have plus something. There's one more change. The function changes when t is equal to 9. At 9, we go from minus 1 up to 1. We're going to be going up 2. So we want plus 2 u9. And that is the answer to this problem. Start at 2, then plus 3 u4, minus 6 u7, plus 2 u9. Let's do another one. Write the function f of t is equal to first t, then t minus 1, then t minus 2, and then 0 in terms of the unit step function. Let's start with a graph of this function. The first part is y is equal to t, and then there's a jump or a discontinuity, a change, some sort of change, and then we have a little piece of y is equal to t minus 1, and then there's another change or jump. We have a part of y is equal to t minus 2, there's a jump at when t is equal to 3, and then the function is equal to 0. So to say this again, we're starting with f of t is equal to t, and then the function changes when t is 1, 2, or 3. So we're expecting our function to look like this. It's going to start with t plus something multiplied by u1, because there's a change happening at 1, plus something multiplied by u2, plus something multiplied by u3. What are these somethings? What are these jumps? At each one of these jumps, we're going to be calculating function on the right minus function on the left. So at the first jump, the function on the right is t minus 1 and the function on the left is t. First jump is t minus 1 minus t, or minus 1. Now this makes sense. The functions have the same it's the same type of function on each side of a jump, but we're just shifting down 1. So it makes sense that the first jump is minus 1. At the second jump, the function on the right is t minus 2. The function on the left is t minus 1. So we do t minus 2 minus t minus 1, or minus 1. And again, this is just a number. We have the same type of function. It's just a line which is sloping upwards. All we're doing is we're shifting downwards by 1 unit. So it makes sense the second jump is also minus 1. What's happening at the third jump? Also we're going down, but it's not the same type of function. The function is not sloping up like this, so the third jump is not minus 1. It's going to be more complex. Let's calculate it. On the right, we have 0. On the left, we have t minus 2. So we do 0 minus t minus 2, or 2 minus t. Okay, so put these in. Our function is t minus u1, because the first jump was minus 1, minus u2, because the second jump was minus 1 again, plus 2 minus t u3, because the third jump was 2 minus t. We'll come back to this function later. One more example. Write this function in terms of the unit step function. The function is t squared, then it's 4, and then it's for e to the power t minus 3. And it looks like this. This function is a continuous function, but still we're having the functions changing at 2 and at 3. So I'm still using this jump notation. What does the function look like? Starts with t squared. There's a change happening at 2, and then there's another change happening at 3. So it's going to be t squared plus something u2 plus something u3. The first jump is 4 minus t squared. 4 on the right, t squared on the left. The second jump is function on the right minus function on the left. So 4 e to the power t minus 3 minus 4. Okay, so we've been talking about this step function. We've been just writing out more complicated function in terms of the unit step function. But this is a chapter about the Laplace transform. And what is the Laplace transform of the unit step function? To calculate this, we're going to use the definition of the Laplace transform, which I've written at the top of the slide. We're going to calculate that the Laplace transform of UC is the integral from 0 to infinity, e to the power minus st, unit step function, dt. Now, this unit step function is either equal to 0 or it's equal to 1. Remember, between 0 and c, the unit step function is equal to 0. And then between c and infinity, this unit step function is equal to 1. Of course, the integral of 0 is just 0. So the first one we can forget about. We need to calculate the integral from c to infinity of e to the power minus st dt. And it turns out that this is e to the power minus cs divided by s. This is an important formula, so let's write this as a theorem. The Laplace transform of the unit step function is e to the power minus cs divided by s. Next idea. Now let's suppose we have a function defined on the positive real numbers. And this could be any functions. I've chosen to draw a function which goes up and down, but it doesn't have to be, just any function you can think of. And take your function, your any function, and shift it to the right by c units. More precisely, I want to define a new function called g, which is equal to f of t minus c, if t is greater than c, and then just to fill in the gap, to fill in what happens between 0 and c, I'm just going to define the function to be equal to 0 here. So we've got a function which starts at 0, and then there's a jump at c, and at the jump we calculate function on the right minus function on the left. So in other words, g is 0 plus the jump multiplied by uc. And of course the jump is just f of t minus c on the right and 0 on the left. So we just get uc f of t minus c. What is the Laplace transform of g in terms of the Laplace transform of f? Let's calculate this. Again, using the definition, we want the integral from 0 to infinity, e to the power minus st, uc, f of t minus c. And as we did before, we only need to calculate the integral starting at c, because uc is equal to 0 between 0 and c. After c, the unit step function is equal to 1. So our integrand becomes e to the power minus st, f of t minus c. Okay, let's do a substitution. For an integral like this, we might like to substitute a new variable, let's say u, instead of t minus c. And of course, du is the same as dt, because du dt is 1. If t is equal to 0 to c, that's true if and only if u is equal to 0. So our integral becomes, instead of starting at c, instead of starting at t equal to c, we start at u equal to 0. Instead of f of t minus c, we have f of u, but instead of e to the power minus st, we have e to the power minus s, and now u plus c. But that's okay, we can calculate this, because we can just take e to the power minus cs outside of the integral. We're integrating with respect to u, so c is a constant, s is a constant in terms of the integral. But what's this? The integral from 0 to infinity, e to the power minus su f of u du. This is just the Laplace transform of f. So we find that the Laplace transform of g is just e to the power minus cs multiplied by the Laplace transform of f. This is an important formula. We're going to be using this a lot, particularly next week we're going to be using this. So let's write this as a theorem. You can find this on your table of elementary Laplace transforms. The Laplace transform of uc, f of t minus c, is equal to e to the power minus cs capital F of s. Right. This function which we looked at before, find the Laplace transform of this function. We've written this in terms of the unit step function. It looks like this. Laplace transform of t, easy. Laplace transform of u1, easy. Laplace transform of u2, easy. But what about this final term? We have our formula for the Laplace transform of uc f at t minus c. But this only works if these numbers are the same. And we don't have that here. We have a 2 and we have a 3. So we're going to need to fiddle with our function just a little bit to make these numbers the same. I'm writing my function like this. T minus u1 minus u2 minus u3 minus u3 t minus 3. Now I can use the formula at the top because I have the number 3 and the same number, the number 3. So I can use the formula at the top of the slide. The answer is 1 over s squared minus e to the power minus s over s minus e to the power minus 2s over s minus e to the power minus 3s over s, and then e to the power minus 3s over s squared. Find the Laplace transform of this function. Function is equal to sine t if t is between 0 and pi over 4, and then the function is equal to sine t plus cos of t minus pi over 4 if t is greater than or equal to pi over 4. Now we can think of our function as sine t plus g of t, where g of t is equal to 0 and then cos, or in other words, g of t is u pi over 4 cos of t minus pi over 4. Okay. So we want the Laplace transform of sine t plus the Laplace transform of u pi over 4 cos t minus pi over 4. And we can do this because these numbers are the same, pi over 4 and pi over 4. We can use the formula at the top, this shifting formula that we've just proved. Because instead of doing the Laplace transform of u pi over 4 cos of t minus pi over 4, we can do e to the power minus pi s over 4 multiplied by the Laplace transform of cos t. This is the key step, so I'm going to repeat this. Instead of u pi over 4, we can take this outside of the Laplace transform, and it becomes e to the power minus pi over 4s. And then instead of cos t minus c inside the bracket, it just becomes the Laplace transform of f of t, or in this case, the Laplace transform of cos t. And this we can write down. We know the Laplace transform of sine, we know the Laplace transform of cos. So this is what we have. We're going to be doing this trick lots and lots of times. Find the inverse Laplace transform of 1 minus e to the power minus 2s over s squared. And the solution looks like this. We want the inverse Laplace transform of 1 over s squared. That's easy. That's just t. Minus the inverse Laplace transform of e to the power minus 2s over s squared. We use our shifting formula for the second term. Anytime we see e to the power minus cs, we think, okay, it must be uc. And we calculate the inverse Laplace transform of what's left. We're left with 1 over s squared. We know that the inverse Laplace transform of 1 over s squared is just t. But instead of the function just as t, we need to replace it by t minus 2. So we have our shifted function t minus 2. That's a good answer. We could leave the answer like this if we wanted to, or we could choose to write this as t if t is between 0 and 2, or 2 if t is greater than 2. And what about e to the power ct f of t? What is the Laplace transform of this function? You can put this in the formula and calculate this. I'll leave this for you to check. And we find that we get capital F, but evaluated at s minus c. Again, this is an important formula which we're going to be using, so write this as a field. The Laplace transform of e to the power ct f of t is capital F at s minus c. And you will see this on your table of elementary Laplace transforms. We're going to be using this next week. We're going to be using this now as well. Find the inverse Laplace transform of 1 over s squared minus 4s plus 5. Now, for a function like this, we don't use partial fractions because s squared minus 4s plus 5 does not have real roots. Instead, we complete the square. So instead, we're going to write this as 1 over s minus 2 squared plus 1. And then we're going to use the formula at the top. If capital F is 1 over s squared plus 1, then we have that capital G is capital F at s minus 2. We want to calculate the inverse Laplace transform of capital F at s minus 2. From the top, we know that that must be e to the power ct, small f at t. Now, what is the inverse Laplace transform of capital F? It's just sine t. We need to multiply this by e to the power 2t. Therefore, small g of t, which is the inverse Laplace transform of capital G, which is the inverse Laplace transform of capital F at s minus 2. Using the formula at the top, that's e to the power 2t, inverse Laplace transform of capital F, or e to the power 2t sine t. Okay, so how do we find the inverse Laplace transform of a rational function like this? The first question to ask is, does the denominator have roots in the real numbers? If the answer is yes, then we want to use partial fractions. Factorize the denominator and then use partial fractions. And then take the inverse Laplace transform of each part. What if the answer is no? If the answer is no, if we don't have real roots, then we need to use this new method. We need to complete the square. And then we're using this second shifting formula. The Laplace transform of e to the power ct f of t is capital F at s minus c. Let's look at two examples. Find the inverse Laplace transform of 30s plus 440 over s squared plus 32s plus 240. Now, first, what are the roots of the denominator? The roots are minus 12 and minus 20. So we're going to be wanting to use partial fractions. And in fact, we can write this function as 10 over s plus 12 plus 20 over s plus 20. Why these numbers? Just because the first time I taught this example was on the 10th of December 2020. So that's why I chose this function. I'm going to leave this example for you to finish. Final example of today's lesson. Find the inverse Laplace transform of 10s plus 12 over s squared plus 40s plus 420. First, we ask, what are the roots of the denominator? And actually, they're complex numbers, minus 20 plus or minus 2i root 5. So we don't want to use partial fractions. Instead, we want to complete the square. And it turns out that our function is 10s plus 12 divided by s plus 20 squared plus 20. Because again, the first time I taught this example was on the 10th of December 2020. Now, how can we break this up? We want to break this up into things that we recognize. For the first bracket, I want s over s plus 20 squared plus 20. Why? Because I know that s over s squared plus a squared is on my table of elementary Laplace transforms. And that sort of looks something like this. For the right bracket, I know that a over s squared plus a squared is on my table of elementary Laplace transforms. So I want to keep a square root of 20 in here, so that the number on the top is the square root of the 20 on the bottom. And then what numbers am I left with? I'm left with 12 over root 20. So that's why I'm taking the 10 out and I'm taking 12 over root 20 out. Now we could write this as 10 multiplied by capital F at s plus 20 plus 12 over root 20 capital H at s plus 20. Where capital F is this function we recognize, s over s squared plus 20, and capital H is root 20 over s squared plus 20. And that's another function we recognize. We know the inverse Laplace transform of capital F and capital H. Of course, they're just cos root 20t and sine root 20t. So what do we have? And there's a typo here. This should be square root just here. Capital G was 10 capital F plus 12 over root 20 capital H. So small g is 10 inverse Laplace transform of capital F plus 12 over root 20 inverse Laplace transform of capital H. And we're going to be using this second shift formula, because the inverse Laplace transform of capital F at s minus c is just e to the power ct f of t. So instead of inverse Laplace transform of capital F s plus 20, we have e to the power minus 20t outside, and then inverse Laplace transform of capital F. And we're going to do the same thing for the second bracket. Instead of the plus 20 just here, we take e to the power minus 20t outside, and then we're just doing inverse Laplace transform of capital H. And we know these two, so we can write down our answer. 10 e to the power minus 20t cos root 20t plus 12 over root 20 e to the power minus 20t sine root 20t. And that is the end of this week's lesson. Next week, we're going to finish talking about the Laplace transform. We'll talk about ODEs with discontinuous forcing functions. We're going to be looking at differential equations which include the unit step function or combinations of the unit step function. And then we're going to be looking at the convolution integral. These two sections are quite difficult. And then at the end of next week's lesson, I'm going to start talking about Chapter 5. And these are just going to be an introduction. This second part of next lesson, this is going to be easier. We'll save the more difficult part of Chapter 5 for the following lesson. So next week is going to be a difficult start, and then the ending will hopefully be easier for you. Are there any questions?